A few years ago, I spoke about Cortical Labs and the headlines they made with DishBrain, 800,000 neurons grown on a microelectrode array, and taught how to play the video game Pong. Now, back then, it was a striking demonstration of goal-directed learning. A tiny wetware organism hitting a pixel back and forth like a microscopic Wimbledon champion. But it seems they've now gone and leveled up because their lab-grown brain is no longer satisfied with Pong and has moved into the realm of Doom, a 3D maze full of corridors, enemies, and split-second decisions, which, if you're old like me, was edge of your seat action back in 1993. Of course, if this were just about getting Doom to run on increasingly ridiculous hardware, it would be a fun party trick. We've all seen the YouTube videos of it running on a pregnancy test or a potato-powered calculator. But what Cortical Labs is aiming at is something much bigger: biological computing, a platform where researchers can literally send code to neurons and watch how they learn in real time. Which brings us to the question of why, especially when we're spending trillions on AI and depleting the world's resources along with it. Why bother with a dish full of cells when NVIDIA have already given us GPUs? Well, that's because in many cases, biology is better. A human brain, for example, runs on about 20 watts of energy. That's less than a dim light bulb, and yet it still handles perception and motor control and language and planning and even the emotional roller coaster of a Monday morning. They are massively parallel, they are energy efficient, and they are capable of learning from tiny amounts of information. If we can harness even a fraction of that efficiency, then we might unlock new forms of computing, systems that are not only powerful, but sustainable, and systems that don't require us to boil the ocean just to train a chatbot. And it's not really about video games either. Doom is simply a controlled and endlessly repeatable environment. It's complex enough to require navigation and threat detection and decision making. Yet it's constrained enough to quantify performance and compare training strategies. Which brings us to the last niggling question of ethics. At what point does a network of cells deserve moral consideration? If a dish of neurons can learn, can they not suffer? And if they can suffer, is it morally acceptable to make them run around a labyrinth being chased by monsters? Of course, scientists are quick to point out that these cultures are far from conscious. They haven't been scooped out of someone's head or plotting their escape through the nearest USB port. But they are adapting. They are changing their firing patterns, which is arguably the very essence of intelligence. And that's why the Doom experiments are so important. They sharpen the conversation. They force us to think about where we draw the line, or at the very least, who gets a say in drawing it. Because if we're bold enough to build systems that learn, adapt, and surprise us, then we need to be bold enough to decide what kind of world we want them to grow into. Not later, not when it's convenient, but now, while the future is still small enough to fit in a Petri dish.